the last class, we have seen directivity and gain of an antenna. Now, if we again recapitulate that both directivity function and gain function, they characterize an antenna's directional behavior. That means, in various directions in space, how much power it radiates. But there is a subtle difference between them that in the last lecture we did not bring out. So, today we will start with that if we look at the numerator of both directivity function and gain function, they are same. That is, at that specific angle what is the radiation intensity, but their denominators are different. That in case of directivity, the denominator is power radiated by isotropic antenna, and in case of gain, it is power input to an isotropic antenna. So, to remember that, basically one diagram becomes helpful. That is, suppose I have a radiating antenna, so we can say that this plane here, we can call this as the something like output terminal of an antenna, because after this the wave is being launched in free space. So, this is basically the directivity's reference. That means, in the denominator of directivity function, basically we say that power radiated by an isotropic radiator, that means this radiation is taking place here. So, this plane is the directivity's reference, whereas this will let us see that this is the transmission line and this is the start of the antenna. This also we called input terminals of the antenna, input terminals of the antenna. So, this at this point, this is the gain reference plane. So, gain is reference here, that how much power is given to an isotropic antenna. So, that means what is happening. So, power is coming here, then power is radiated from here. So, in between here what can happen? One thing you see, that while giving this power, some power may gets reflected. So, that is a mismatch. So, that is not present in the directivity thing. Similarly, some power may be lost here, that is also not present in the directivity thing. So, that is why we actually relate this gain function theta phi, that can be related to directivity function theta pi if obviously they are proportional. The proportionality constant is efficiency. So, you see that gain actually takes care of all these efficiencies. Now, there are several efficiencies that comes into play. So, one by one we will see them. That the first efficiency that can come is, as I said, that there is a transmission line and then the antenna is getting started. So, this is the input terminal of the antenna, generally we call this the input terminals. So, here if there is an impedance mismatch, then there will be some reflection. So, this reflection due to mismatch, due to that there will be an efficiency. So, this we generally call rho r, the reflection efficiency, and this in power terms, generally if voltage reflection coefficient is gamma, then 1 minus gamma square or 1 minus gamma into 1 minus gamma star, whatever. So, that is So, here this that means we can say reflection efficiency. So, this is one part of the efficiency. That means, if I now say that this let us then use the symbol rho. So, I can say that rho will be something like rho r into something that will come one by one. The second part will be that in the antenna, there are some metallic structures, some conductors. So, obviously, if electrons flow from there as a current, then there will be some resistance. So, there will be some loss. So, that we can say that if this is the antenna, then there will be the conduction current flowing here on the metallic structure. So, that will give rise to the, we can say this is the conduction current IC. So, this will give rise to an efficiency which is conductor loss. And later we will see how to calculate this conductor loss. So, this is basically we can say that conductor efficiency, basically I square R loss in a conductor, in a metal or in a conductor. Similarly, there will be power dissipation in the dielectrics, like even if nothing is there, there are air dielectric, or in many antennas there are various dielectrics. So, there will be the displacement current through them, and I can say again that there will be currents which are basically I can say the dielectric current I d. So, there will be also in between dielectric currents I d. So, due to that there will be the loss. So, dielectric efficiency, etc. So, now I can complete these, that rho will be rho r into rho c into rho d, but there will be another, actually that we have not talked of, but later we will see that antenna has a polarization. So, if we if the antenna is not if there is a mismatch in the polarization of the wave coming and polarization of the antenna, then there is a polarization mismatch loss. So, that we will discuss later, but here I introduce that term, that there will be another one, that due to the polarization mismatch, if polarization is matched, then there will be maximum power can be extracted. So, polarization mismatch loss, this is PLF. So, this gives rise to an efficiency which is called rho PLF. So, finally, we can say that rho is nothing but rho r, rho c, rho d, rho PLF. Here I want to say that already we have discussed this. Now, this gamma is well known, that if from this antenna's end, suppose the antenna is giving an impedance Z A and the characteristic impedance of this transmission line is Z naught, then we know that the reflection coefficient gamma will be Z A minus Z naught by Z A plus Z naught. So, from there we can calculate voltage reflection coefficient, and from there we can find what is the power loss. So, these are things that was not said. So, that means gain it is a more useful quantity compared to directivity, though both gives the directed nature, both characterizes the antenna's directed nature, but the gain that also takes into account these efficiencies. So, ultimately at the end of the day I understand that how much power I have given and how much it was able to actually give. Now, a related term is there sometimes transmitter people, because you know any antenna actually in the transmitting mode it is connected with a transmitter. So, the transmitter people sometimes use another term which is related to this gain, that is called EIRP, effective isotropic radiated power, EIRP. Now, what is the concept of EIRP? That it is a product of the input power given to an antenna and the gain of the antenna, because at the end of the day it says that in a particular direction, suppose I have a transmitter and that transmitter has a antenna. So, that antenna has a gain. So, in a particular direction, let us say this, at this direction this gain is G. So, ultimately if this transmitter is giving me power PR, then I am getting a power from here in this direction effectively as PR into G, as if, that is why this isotropic term comes, as if I have an isotropic antenna. So, total power given is PR into G. For a actual antenna the power is given PR, but it is getting multiplied by the gain because it is a spatial gain. So, in this direction power is being jacked up by that amount, but this term says EIRP. Now, why transmitter people use it, or you will see the space scientists they generally use this, because suppose I have an antenna with 1 watt power and gain of 10, and another transmitter system I have where I have 10 watt power, but gain of the antenna is 1. Now, both of them are actually giving effectively same thing, because one is having a higher power transmitter power, but the gain is less. So, effectively these two are same. So, they actually make these two equal by incorporating these two things in the product. Actually, for link budget calculation this is sufficient, but if you are interested for a designer, this is not a good parameter, because we want to have more gain to an antenna. So, same EIRP, you see in both these cases same EIRP, but obviously one antenna is much better, 10 times better in gain than the other. So, obviously that is a better design as far as antenna is concerned. So, antenna people do not use this EIRP term much, but as a link budget calculation you should see this. Also, we have discussed the various these efficiencies, particularly in case of the current element. That time we have seen that the current element is a very inefficient radiator. We have taken 2-3 numerical examples to show that. Actually, the reason is, one of the reason is this, actually this gain function, this is dependent on various parameters of the antenna. Now, one of that is the size of the antenna, electrical size of the antenna. Now, current element is a very small size antenna. Also, we will see that planar antennas etc., there also there is a term which we have not introduced now, that is called effective area. So, that is also again electrical effective area. So, if any antenna is not having sufficient electrical area, its efficiency will be poor. Now, next we go to another important parameter, that is of antenna, that is called half power beam width. Now, you see this also, because generally we have seen when the radiation pattern of an antenna that there is a main beam generally associated with each antenna. So, most of the power is concentrated into the main beam. So, that is why how wide is that beam, that is an useful criteria. So, if I have a very short beam, but I have sufficient power, then that is good, that means the antenna is very directive. So, that is why people have come out with this, that suppose this is the main beam, obviously there are side beams, I am not drawing that. Now, from here, and let us say that in which plane I am seeing this pattern, because we have seen pattern is a 3-dimensional pattern, but this pattern is in a plane where I have the maximum direction of radiation. So, in a plane containing the direction of maximum of a beam, the angle between two directions. So, I draw two directions. How I draw these two directions? This is the maximum radiation direction. Now, I locate, usually we locate that power wise, where from maximum I have half power. So, this is one point where I have half power, this is one point where we have half power. So, this angle between them, that is called half power beam width. So, I can from the radiation pattern I can find the main beam, I locate the maximum, and from maximum I locate the 2 points in the two sides. Usually the main beam is symmetric about the maximum thing, symmetric, or at least it has two sides. So, there we locate at the angle between them, that is called the half power beam width. Also sometimes this is called 3 dB beam width for obvious reasons, because half power in power, if I have a half power, that is 3 dB. Now, actually we could have some other points also, like sometimes people say 10 dB beam width. 10 dB beam width means that whatever power we have, instead of locating the half, if I locate the 1/10 power of the maximum. So, if this point is 1/10 of maximum, this point is 1/10 of maximum, then this angle will be called 10 dB beam width. Sometimes we also say null to null beam width. Null to null beam width means one null and another null. Suppose generally if we have things like this, so this is one null, this is another null. So, these angles are null to null beam width. In the polar plot, you see this direction is a null, this direction is a null. So, this total angle is a null to null beam width. So, usually like this. If nothing is specified, when loosely only we say beam width, that should by default means this half power beam width or 3 dB beam width. Now, there is a related parameter that okay, I know that what is the main beam's width, but how much efficient I am, because how much energy I am wasting in the side bands and how much I am efficiently putting into the main beam. So, that parameter is called beam efficiency. So, what is beam efficiency? You see, whatever I said, the power transmitted within main beam divided by power transmitted by the antenna, that means including side lobes, etc., everything. So, mathematically how to tackle this? You see, it is easy. We know that if U theta phi is the radiation efficiency, then if I multiply this by solid angle and if I take appropriate ones, then this same expression by taking the proper limits I can get it. Now, what already we have seen that what is d omega? D omega is nothing but sin theta d theta d phi. So, I can put that sin theta d theta d phi. Now, what is main beam? You see 0 to 2 pi I can do, and here I can very easily do beam width by 2. You see, if I do this, since I am taking from 0 to 2 pi, I am actually in elevation plane. If I have a beam width theta b, then 0 to theta b, this is the power in the main beam. And what is the power here? Here you take all the points. So, all possible angles 0 to pi, that will give you actually the beam efficiency. So, basically we require in particularly when for radio astronomy or radar radiometry, where you have you need to very efficiently use your power, that time this beam efficiency should be of the order of 90% or more, particularly radio astronomy people, because they are getting very feeble response from a radio star, etc. Now, if they cannot put it into the main beam, then they many times won't be able to detect it. Similarly, a radar, it will have to pinpoint its maximum power into the target direction. It should not unnecessarily use it in the side lobes, etc. That will cause interference, and also it will have problem in detection, etc. So, that is why beam efficiency is one of the specification of the antennas. Now, next comes another specification. It is for any electronic system, this is important, that is a related term, do not get confused, it is bandwidth. So, we have seen beam width, now we will discuss about bandwidth. Now, what is bandwidth definition? Bandwidth is range of frequencies within which the performance of the antenna with respect to some characteristic, like whatever we discussed, that we have discussed various parameters. So, those some of those parameters conforms to a given standard or specified standard or specification. So, I can say bandwidth is nothing but a range of frequency within which the antenna performance is satisfactory. Now, what do I mean by this? You see that suppose gain is an important parameter for antenna. So, I can say that okay, gain of the antenna within this range of frequencies within which gain should be at least let us say 10 dB. So, that will be called a 10 dB frequency bandwidth. Now, for wideband antennas, nowadays this we require wide bandwidth, because various a particular signal, its band is getting increased. So, we want wide bandwidth. Now, in that case always instead of this range, sometimes we say that for I will say wide band things, instead of range of frequencies, we say the upper frequency by lower frequency. Range is the difference between upper minus lower, but if you divide upper by lower, so sometimes you will see that a wideband antenna, people say bandwidth is 10:1. That means upper frequency of operation, satisfactory operation, by lower frequency of satisfactory operation, that is 10:1. Narrow band antennas, for them generally there is a center frequency. So, within the range of frequency, acceptable frequency, there is a center frequency, and people specify that about that center frequency in both sides how much you can go. So, people say 5% bandwidth. Now, what is the meaning of 5% bandwidth? 5% bandwidth means frequency difference of acceptable operation is 5% from the center frequency of the bandwidth, 5%, 10%, etc. Actually, the point is that antenna characteristic, if you take frequency response of antennas for various characteristics like gain or suppose impedance, etc., etc. So, they are not vary equally in the all. So, gain has a particular frequency response, impedance may have another frequency response, etc., etc. Pattern may have another frequency response. So, that is why, so we will have to say when we are saying bandwidth, now what bandwidth we are talking. That is why you will see that people talk of impedance bandwidth. That means antennas impedance should be at least within, let us say that how much ohm, or sometimes VSWR is a measure of impedance with respect to a standard, particularly the characteristic impedance of the transmission line. So, impedance bandwidth is a term. That is why you will see that many antennas people characterize, okay, the 10 dB impedance bandwidth. That means, or VSWR is, or reflection coefficient 10 dB. So, actually that is a characterization of impedance bandwidth. Similarly, there can be pattern bandwidth, etc., but all has this same thing, that what is my acceptable frequency range, where the thing that is the antenna parameter that is specified, that is acceptable to me, or that is within a specification. Okay. The next concept that will come is another important concept that is called polarization, but I think for this time is up. So, we will need to see it in the next one. So, in this lecture what we have seen is that what is actually the concept of efficiency in antennas, particularly what is the subtle difference between gain function and directivity function of the antennas. So, there we have seen various efficiencies, and after that we have seen the concept of beam width and concept of bandwidth. So, these three antenna parameters we have seen in this lecture. Some other more antenna parameters we will see in the next lecture. Thank you.